In this video, we're going to compute the flux across a surface S that is oriented, though using a slightly different technique. So we're going to revisit a problem we saw earlier. There are a couple corrections here. I'm just going to whiz through these slides and just point out that I've corrected the cross product of the two vectors really is just 1, 0, 0. So the normal vector you use should either be the plus or minus version of this vector. Which one do you use? You've got to look at the picture to determine. So in this case, the outward vector, we're going to use this 1, 0, 0. Same deal here. The cross product itself for the back, you get 1, 0, 0, but which vector do you use? Well, the vector points that way, so we need the negative here. And don't try to memorize anything. You really should go off the picture, because had you switched the role of u and v, well, you'd probably use the plus here. I mean, just go through and compute that. Also corrected here in the previous set of slides, that was a positive one. This is now a negative one. Correctly didn't matter because we got a 0 anyway, because x here was 0, so that didn't really matter. But otherwise, same thing here. The cross product itself is listed correctly, and for the normal vector you have to use one or the other. The vector that is the cross product, or it's negative. And same thing for the left side. It's just you need the negative of the cross product vector, and same thing here. And same thing here. Now this, not that any of this work was really so hard to do, but some of these 6 integrals, it was still quite a bit of work, pretty tedious to set up. And the whole point is that there's another way to do this, which is to use the divergence theorem. So since S is the boundary of this rectangular prism, to find the flux across the surface S, well, you either write your flux this way or this way, but either way you write this, the divergence theorem says that your surface integral, which is a flux, converts into the triple integral over the divergence of the vector field. So let's just compute, right? So the divergence of f right here, partial with respect to x is 2, partial with respect to y is 0, partial with respect to z is 0, so you just have 2 plus 0 plus 0. We're just integrating 2 right here. And what about e? Well, x goes from 0 to 4, y goes from 0 to 3, and z goes from 0 to 2. So this is a really nice integral. In fact, you can just bring the 2 out in front, and you're just always integrating ones, so you just have that multiplier of 2 times the 4 times 3 times 2, which is 48.